Thanks, Christian. So it's a pleasure to have the opportunity to speak to everyone. It's really nice to be back after several years. I also spent a few years at JK Tech, so that gave me an interesting perspective on what we do here at JKMRC and the production centres in terms of getting stuff out into the industry and providing industry with solutions at a consulting level, not just the research level. Despite this being a relatively short notice, this is something I've sort of wanted to discuss, and after this discussion and presentation, I'd love for questions, but also afterwards for people, if they have discussions or ideas or comments, to come to me and talk to me about it, because this is one perspective I'll be giving on the difference or the subtleties between electronic, digital and virtual. It's not my view, it's the view of most digital heavy consultancies and software companies and other industries, but it'd be interesting to see what we think in the mining and mineral space. So before I start getting into it, I also want to apologise in advance for presenting a lot of Dassault System stuff. I don't want this to be a plug for Dassault System, but it just happens to be that I have a lot of material from Dassault System. Therefore, there will be some slides and certainly videos that are Dassault System heavy, and some of them have a slight marketing twinge, so I apologise for that in advance. Let me get this thing. So nevertheless, this is what the presentation is really about. One view of the difference between what it means to say something's electronic, digital and virtual. And I'll try to start exploring how that applies to our industry and importantly our research. And I think I'll be challenging and asking you to ask yourself some questions as to what the research might be here. And we'll get to that as we go along. So I want to start with the idea of getting on a plane and you've got a little ticket in your hand. And of course that ticket is usually a boarding pass. Now often these days we've got mobile phones and we sometimes PDF our boarding pass and send it to ourselves via email, and we've got our boarding pass on our phone. If it's a PDF, that is an electronic copy. Why is it electronic? Because it's an electronic form. But if the gate changes, or if for some reason our seat changes, we don't see that on our PDF. It's not digital. It's not connected. It's not a digital representation of this. I better stand in front of the camera. It's not a digital representation of our boarding pass in the sense that it's up to date. It's just a copy. However, some airlines are now starting to provide digital boarding passes. So they change. So if the boarding pass changes, if the gate changes, if your seat changes, if something else changes, the aircraft changes, it might send you a little update onto your boarding pass. It might send you an email or a text as well, but the boarding pass itself on your phone will change. That is digital. It's connected. It's live. Now when we're starting to talk about virtual, the key difference, according to many, between digital and virtual is about experiential. There's a behavior involved in something. So you might argue, and our boarding pass is a very simple example, but nevertheless we can see that a boarding pass, our phone becomes a virtual boarding pass. The phone acts like a boarding pass. Similar, you can see a smartwatch here acts like a boarding pass. But as I said, a boarding pass is a very simple example. If we start talking about engineering systems, the difference there between digital and virtual starts becoming, is it a digital representation of something, or does it behave like an object or something? That's the key difference. Virtual is experiential, it's behavioral. It actually represents how something behaves. I'll come back to that in a little bit more detail on the next slide. But I wanted to raise this because this point is happening quite a lot also in mining as well as other industries. There's a lot of what I call players or actors in the market in our industry and in other industries that's saying they're digitizing stuff. They're digitizing the mind, they're digitizing equipment, they're digitizing this and that. Most of them are digitizing the data, not the object. And that's a very subtle difference, but it's important. They are digitizing these objects, but they're not capturing the essence of that object. And let me go into a bit more detail. I've got this diagram here. It's just a database that captures numbers related to the object. Might be size, dimensions, might be where it's acquired from, the vendor that supplied it, what time it was purchased, by whom, where it's sitting in our organization. Is it sitting on mine site A? Is it sitting in warehouse B? Those data are digitized often, but it's not the essence of the object. Because if we're to replace that object, how do we do that? How do we know what to replace it with? If the part numbers are different from another vendor, if the dimensions might be a bit different, how do we do that? One of the key things of truly, fully digitizing an object is to get that 3D representation. And I would argue that proper digitization or full digitization of an object requires 3D representation. It's not the be-all and end-all, but it is a very critical, important part to fully capture an object in the digital space. So just to summarize, and now we're going to, let's leave the whole idea of our boarding pass and look at potentially a whole mine or a plant or a resource. Electronic representation of that might be a bunch of 2D files that are now in electronic form, whether they're PDFs or whether they're scans. There could be anything like that that's not connected and digitized in the sense that we can update it easily. We might not even be able to search it easily. Digital, we're now starting to talk about preferably a 3D representation with a variety of information regarding that, where the numbers are linked to the 3D representation. And once we start moving into the virtual space, we start talking about a system that's to some level experiential, in the sense that you can experience. So we're all familiar with virtual reality. We put our goggles on, we see stuff, we experience it. That's virtual. It's a virtual space. It reacts to us. It's behavioral. We might simulate it. So we do something to it, we give it an input, and it behaves. Now we're in the virtual space. And preferably also, as mentioned here, interactive. And one of the key things that's really important to capture that virtual system effectively is we start needing to take into account systems thinking, how the different systems relate to each other. And that's something that I would suggest in mining, in particular, we're not used to doing very well, very much. We're not used to looking at the electronics system or the electrical system that powers our equipment. We just assume it's there. We're often not even looking at, and we're starting to, this is really exciting, we're not often looking at the movement of material between individual equipment and how that behaves. We just assume it's there and it's passes the material from A to B. We're often not looking at external influences, and I'll touch on those as we go on. So again, this is where we have been at JK traditionally, and this is a fantastic place to start. So there's a road ahead of us, but this is a great place where we have built a really strong capability and reputation that we have been digitizing and to some extent virtualizing our equipment. But we've been focusing on individual equipment. Generally, we connect the equipment together, sure. But we've been focusing on the individual equipment. We've been looking at steady state. Great start again. One of the key issues with steady state is that it shows how equipment or a plant can behave and should behave, ideally. But I would argue 95% of the time or more, that's not how the plant behaves. but it's a very important area because the steady state that we model here at JK and the SMI, traditionally, is a really great place to target the operation. So when we start looking at dynamic models, we can target that steady state. We can say, this is where we want to be operating. Not exactly, but close, because we know how things should operate. And of course, traditionally so far, we've been dealing with 2D. And that's fine, but one of the things that 3D brings is it brings a different perspective on will it work. I wonder how many of us in this room have run simulations and models on SimNet, SimFloat, whatever it is, and thought, will that bin overflow? Will we get spillage? We might have a number saying the throughput has doubled, or we've got twice the amount of concentrate going on over our cell. We might have some data saying how big that drum is and how it will overflow, but we might not. Also, will we have access to that? If we put a pipe there and move that pipe from here to here, we do that on SimFloat all the time. I used to run a JK Tech and say, okay, let's change this flow from here to there. Is that even possible? If we walk onto the plant, we say, what if we don't have to walk onto the plant? What if we've got a 3D representation of the plant and say, look, that pipe is going to be a real pain in the neck to put in. Really important. Now, we haven't just done individual equipment, and we haven't just done individual parts. And of course, JKMRC is at the forefront of the IES model system. And this is my little thing here. I'll put this in because this is SEE, Sustainability and Extraction Efficiency. I was very heavily involved in this project, from which IES evolved. And this is an example of how we're starting to think systems thinking. We're connecting, making sure I've got the right buttons, the geology, the blasting, the movement, the stockpiling in hard metals, the comminution and the flotation in hard rock mining. So we've started on that journey. But even in the system, even in IES, we're not looking at these connections. We're not saying, okay, the trucks are moving, what are the roads like? The pipes in here, what are they doing? Are they going to block up? Are they going to fail? But it's a great start. Fantastic foundation. So I'm just going to play a few videos, as I mentioned. The next couple of videos, they're going to show you what's currently happening across some other industries and what's available to us now, and some of the journeys we might be looking to take. So there's no sound in this one. I'll talk over a little bit. Again, this is Dassault, but I remind everyone that Dassault Systems is not the only company that does this. They would claim they're at the forefront, perhaps they are. But this is about a systems model of a car. I won't tell you which company this is done for, but I will tell you that it's the world's leading electric car company that makes high-performance cars. And I'll just stop it there quickly. I'll bring your attention to this system here. These are separate systems in the car: physical, electrical, mechanical, and they've got lines between them. They're all connected. We're looking at the system of the car. I'll also bring your attention, you can't really read that, but I'll read it out for you. It's requirement, functional, logical, physical. They're all aspects of the system. This is traditional, bog standard engineering design approach. It's called RFLP. Look it up. There's heaps out there on it. And all engineering systems, including our own, take this approach, whether formally or informally. You identify the requirements. In a mine, the requirements might be, we need to produce X amount of gold at this price. It might be a very high level requirement. Functional might be, we need to mine the dirt and we need to get the gold out of it. Very simple, very high level functional. Logical means, well, we're going to have to connect the mine via trucks to the plant. We're going to have to connect the plant via some sort of transport system, and we're going to need an electrical system to drive it, and we're going to need roads. That's the logical system. And the physical is the physical representation, and we do this. We model our underground ore bodies. We model our roads and our mines. They're all parts of the system. So we do this whether we recognize it as a formal RFLP approach. The key here is that all these systems are connected. And you can see here we're looking at 3D representation that's actually got a model behind it. We're just double clicking on the 3D representation, and there's individual systems. There's a wheel, there's a brake, there's a shock absorber, there's a spring. All these systems are modeled. Are they modeled perfectly? No, I'll come back to that later as well. But you can see here that we're simulating. We're simulating the car, 2.9 seconds. That's that special car company that I don't mention. 2.9 seconds, 0 to 100 km an hour. And of course, you can see that the motor here is just a box. It's not a detailed physical representation. They probably have a detailed physical representation somewhere else, but here they just summarize what the motor does. They have some sort of virtual model to say this is how it behaves. And of course, we can start looking at how different parts of the system behave, all linked to the 3D representation. If we didn't have the 3D representation, we might say, okay, let's put bigger tyres on the car. And we might miss the fact that the tyres stick out from the wheel arches. Something simple like that. Now, of course, we can start looking at different systems, and this is now we're starting to look into perhaps our own industry. That's a very simple example of just a digger, but you can imagine that we might have a system of an overall mine. So again, electrical system, mechanical system, transport system. I thought I'd just leave it playing because it's pretty cool, this thing. You can really see here the virtual space. They designed this robot in the virtual space before putting it together, and it does exactly what the virtual space is. That's a simple one. Okay, let's just jump ahead. There's sound to this one, so let's play it.
An interaction of complex systems is a huge challenge for today's engineers.
Is that loud enough?
They're demanding tools that are more natural and intuitive, so that they can better understand the behavior of complex systems. Katevi 6 introduces exciting new capabilities. It uses the power of 3D to interact naturally and understand information that is traditionally hard to access. Let's go through some new advanced features in Katevi 6 systems that enable you to truly experience the behavior of the virtual product. First, let's look at this automotive example, where we want to get a better understanding of the vehicle traction as it performs a number of maneuvers. In addition to the 3D representation of the numerical model, Katevi Systems Dynamic Behavior Modeling provides us with 3D aids to visualize the simulation data, such as the magnitude and direction of forces or torques. Also in this release, new features are introduced that significantly enhance user productivity when working with 3D CAD models that are linked to modelic behavior models. In this aerospace example, we can see a satellite link structure on an unmanned aerial vehicle, where the satellite dish is slightly misplaced. When simulating the modelic model, the 3D satellite structure is initialized according to the mechanical constraints. During the simulation, we see the dish tracking the satellite by moving around in 2 axes. With a single click, the user can choose to apply this permanently to the 3D part, avoiding manual adjustment. Not only does understanding of the systems get easier, but so does the interaction with it. Systems engineers can now define interactive 3D controls for the behavior of their models. This is a simple example of how a system's behavior can be driven by user interaction, as it would be done in real life. This paradigm can be easily extended to monitoring or interactive 2D control panels. This allows systems designers to make simulation more accessible to non-experts, resulting in enhanced user understanding. Katevi 6 offers an enriched product experience in 3D.
As John Lennon said, you may say I'm a dreamer, but I can imagine us having a 3D model of a plant, perhaps even a mine, where we can see a little arrow with the grade of ore coming, changing, and we see the difference, little arrows and so on, of forces or recoveries and grades happening across a plant. We can also see an example here of that flying object where we set a set point with the control system, and we see the control system reacting and the system changing to whatever control inputs are happening. This is an example. It's a long video. I'm going to jump over. I've got a few notes here to indicate what areas. But what I wanted to do here with this particular video is show you how what our traditional thinking of our traditional approach of modelling can link to a 3D model and how that can be very powerful. So this is an example. You might be aware that Dassault Systèmes is running Singapore Cities project. And Singapore Cities project is capturing the whole city in the virtual space. Now, that's a very, very large statement, but it's doing multiple things. It's capturing things such as the infrastructure of the city, how water runs off in this example touches that, how the water runoff of the city, how does it handle flooding, traffic, weather, other things like that. But of course, human traffic, interaction of what happens in the city given big events and so on. But this one, it says start off at 5, so I'll jump ahead to 5, about there. So what they're doing is they've got this model of the city and they're looking at one block, three-dimensional model of one block, and they're saying, okay, what happens during a high rain event? Singapore gets a lot of storms, gets a lot of heavy rain. And linked to this model, 3D model, is what we're used to seeing. A 2D representation of that model, modeling the water runoff. And you can see here, we've got an input on the left-hand side, that's the rain model. We've got some sort of representation of the drainage system, and we've got some sort of representation of a system that gets rid of the water. It might be just natural runoff, but they've also got a pumping station, pumping system. And what they've actually done is they've taken the rain model from the internet. They've literally just gone to the internet and said, what's the high rain, typical high rain behavior in Singapore? And they put that in the rain model and they just simply simulate it. Let's just see what they're doing here. They're looking at the electromechanical aspect. So they've got some sort of system that pumps and provides the pumps with power, bearing, and other aspects. They're playing around. I'll just jump ahead a little bit again. They're playing around with some parameters. And you can see that this is the sort of stuff we're used to, and it's linked to the 3D. It's modeling, hardcore modeling. Here we go. Jump ahead. Just want to jump ahead to show you how the simulator can interact with the 3D space. They're just going to set up, okay, 7, 8, so we just jump ahead to 8. They've set up a little graph saying we're going to graph these couple of parameters. You can't read them here, but I think one's rainfall and one is the level of the runoff. And you can see here, you can read it here. The blue line is rain coming down and heavy, and the red line is the level here. And you can see that it overflows. Not a problem. What they do is they increase the size of the runoff. And you can see that in 3D, they've just got that preset in this particular example. It just gets wider. They run the model again, and lo and behold, it doesn't flood. The key here, and later on, actually I won't show that now, but later on what they do is they say, okay, what happens in a 1 in 100 year rain event? They find that it floods again or gets very close to flooding, so they simply just go to the pump station, and rather than having 3 or 4 parallel pumps, they increase the number of pumps to 6. And now they've got a design for that system given variations in that block. So if they put a new building in the block, they might run a new model. Okay, let's just jump ahead from that. So let's just summarize quickly. We touched on the difference between electronic, digital, and virtual. And now let's just summarize where we are regarding what's happening in digitisation, virtualisation across industries. Key, the RFLP approach. Whether we know we're doing it or we're not aware, that's what we do. The keys are systems thinking and components and connections between them. We're good at doing components. One of our next steps, I'm sure, will be looking at the connections between them and how those behave. And I reiterate, 3D visualization, in my mind, is very important for validation. Some things you just won't see unless you have 3D representation. So I think many of you are probably sitting there thinking, yes, that's very nice. We know exactly how a car motor works or how a generator works, and we can model that. We know how car brakes work. And mining's a bit of a special case. We're more complex. These are the sort of things we hear. With an unbroken flow, we need increase in productivity, quality, the right KPIs. We need to integrate. It's been in mining for 20 years now, and we need to integrate our systems. How effective have we been in that? I'll go further and say, we can't afford to do something different that hasn't been done before and not have it work. Severe pressures. That's why we're just playing, we're dipping our toe. But all those quotes are not from mining. They're from manufacturing and order. That's really important. Every industry thinks they're special. Every industry, now we're different. Mining and minerals are different, but we're not that different. Not to have the same comments and the same expectations of what we can do. Hence, I suggest that simulation of integrated holistic, we often say that. I say almost everyone in mining. I wasn't going to put a name against that. But I would suggest that I'm going to reuse this oft-quoted phrase. Every model is wrong, but some models are useful. Oh, I don't think I embedded this video, so I'm just going to jump out of here and show you this video. What video is systems engineering dynamic? Apologies for that, but hopefully it'll play. Sound?
Systems engineering approach. It now delivers a supplemental suite of multidiscipline libraries that are specifically designed for advanced modeling of complex multi-physical systems. It's particularly beneficial to the automotive, aerospace, robotics, and energy sectors. In this example, we simulate two SUVs that abruptly apply the brakes on a slippery road, which is indicated by the white zone. The SUV on the left is equipped with an anti-lock braking system, while the one on the right is not. Let's focus on how we created the model. The results are based upon the logical modeling of the system in terms of components, and each component has its own behavior. We can see the rear suspension as we zoom into the vehicle dynamics library. The vehicle dynamics libraries model and simulate the complete vehicle, and for this example, we focus on chassis dynamics. The chassis model is based on multi-body mechanics with detailed models of wheel suspensions and tires. The library also contains powerful road descriptions and driver models. This world-leading suite of Modelica lifelike modelization components is now integrated within CATIA V6, so you can realistically model and simulate a variety of field scenarios and drastically improve the way complex interacting systems are engineered.
I'll bring your attention to a phrase she used. We've got models for this and models for this, and powerful descriptions of driver behavior and road conditions. we've got powerful descriptions of our ore bodies. They're not very good, but we can model just about everything else. Pretty well, very well. Do you think they've got a perfect model for the braking system? A perfect model for the suspension? No, it's close, but it's pretty good. And our models of our equipment is pretty good. But they don't have perfect representation of how a driver behaves or how the road behaves. But it's what they call, in phrase, powerful descriptions. That's all we need. Once we get a system, once we get things connected, once we're in a virtual world that's close enough, hence, once a model, once we have a virtual space that's useful, then we can start seeing how things, when things will fail. The industry in aerospace, I've got this up here, aerospace and car. Aerospace, big aircraft manufacturers no longer make scale models of aircraft and fly them or test them in a wind tunnel. They simulate an aircraft flying. No scale models, no 5 to 6 meter models. They build the whole thing after simulating. And they take the first aircraft, they put a pilot in it, and they hope it flies. But the level of simulation, including the mechanics, the electronics, the ventilation, the airflow, all that sort of stuff is there. Do you think that's really less complex than what we're doing in mining? I argue that it's not. There are more complexities in certain parts of mining, but you could argue that there are more complexities in certain parts of aircraft flight that they don't actually have to get right or perfect anyway. This is a video I just nicked off the internet, and so I don't have to quote it because they quote it themselves. It's just a very simple model of a mine working. I think the main point here is that we don't need, as I'm sort of repeating myself a little bit, but we don't need all the models to be perfect. We need the system to be modeled virtually. We need to be able to have it behave, and we need to be able to interact with it and see how it responds in a systems model. So we know when there's not enough power. We know when our conveyor is going to be overloaded. We know when a bin might have too many large particles going in and it's going to get blocked up. And we know when a flotation cell might not be flowing over with flotation because it's sitting too low, or a screen might block up. And once we have that sort of system, yes, we can look at control, ore changes, water environment, social impact, the sort of stuff that we like talking about. We also start looking at the system, not just the mine. We also start looking at, and this is not a full list, but this is the sort of list that we might start thinking about. What's the weather impact of our mine? What happens if we have rain or big rain events? Is there flooding? Will some people struggle to get to site and we'll be short of numbers? Will our temperature affect our flotation performance or leaching performance? Yes, it will. How much? Sometimes significantly, sometimes not, depending on our operation. We might start looking at shipping. Say, we actually don't need to make production this month or this quarter because we know that the shipping lanes or the truck companies are short and we're not going to be able to deliver that to our clients anyway. So why push hard and maybe drive our equipment towards requiring early maintenance just because there's a KPI that's actually not valid for this month or this quarter. And of course that comes into a similar sort of approach from market conditions. What are the prices? Can we react to those prices and know what our approach might be? And of course there's many other considerations as well. So one of our challenges, and I want to bring it back to SMI and the production centres, we've got a challenge is because there's a lot of stuff happening in the space in mining. And mind you, this is a very simple summary. It's not perfect, it's not correct, but it's approximate of what we do to make a mine operational. And we do this over and over, even if it's just an expansion or a modification. We do requirements, we do a quick feasibility study. It might not be a feasibility study for a whole mine, but it might be a feasibility study for a new piece of equipment. And we design engineer it, and we have somebody that constructs it and commissions it, and then we run operations and maintenance. And we've got different players. Again, it's not necessarily correct, but it's a view of what the players are. Where do we sit? Most of the time so far, we've been sitting in this space. To some extent, maybe design. But some of the questions we must ask ourselves is, where do we sit and how do we leverage our capabilities and develop our capabilities into the digital space, into the virtual space, whether we do stuff in there, and we are. Marcin's driving this from the production centres, and he's talking to everybody across SMI and the university. But one of our jobs here is to identify, where do we fit? Do we develop this stuff, or do we somehow use it and utilise it? And how do we develop, and how do we leverage, and how do we promote digital, what many call digital continuity? That the data and the information between these groups and these systems is not lost, because it is lost. Most of it's lost anyway. In manufacturing, that digital continuity is there. Not everybody's got it, but the leaders have it. And they've developed it over the last 20 or 30 years. When somebody designs requirements, they pass those requirements to the feasibility or the assessment group, and that passes on to design. In design, if they make a change and it doesn't align with the requirements, they know. And they know why that decision was made. They've got a very clear line. If our EPC companies, engineering, procurement, and commissioning, by the way, if our EPC companies change a design somewhere along the line, they often miss a key requirement. Happens often. So, I would suggest that one of the things we consider when we're looking at this sort of stuff is, where is the value? And where can we provide the value? This is a very, very simple and highly just a subset of some of the things we should consider. The variability. This is data that I actually grabbed during doing an energy study for a company. And this is the data they gave me for megawatt, the power of mill use. It says no output, but it's the power output of the mill. And I said, yeah, it's pretty steady. It's pretty good. This is over 6 days. And I said, okay, well, that's good. Very good. And they could have given me data over several months. I actually had several months worth of data, but this says 6 days. I said, give me the raw data. So they said, look, we're targeting about 12 and a half, maybe 13 megawatts. Because usually the higher power the mill, the higher power draw of the mill, the more efficient the comminution. They said, we're targeting about 12 and a half, maybe 13. That's our target. But okay, give me the raw data. That's the raw data. That's 5-minute average, every 5 minutes. This is an average over each day. This is the raw data where I've taken the data every 5 minutes. It's exactly the same mill. And you can see here that it's normally, when it's operating reasonably, it's operating at about 15 megawatts, maybe 14 and a half. Variability is a killer in our industry for productivity and value. And if we have a reasonable model, virtual space, when we do our two traditional simulations, we're usually sitting up here where we should be operating. But what actually happens is this. And this is not specific to a mine site, particular mine. Most mines will see this sort of behavior. It wasn't a particularly bad 6 days. It was pretty standard for how they operate. So one key thing to think about is, how do we leverage our approach, our research, perhaps virtual and digital solutions to reduce variability, and how does your work fit into that? Linked but not directly aligned is shutdowns and stoppages. If you can reduce, if you have a shutdown for 3 or 4 or 5 days on a mine to do some maintenance, and you can reduce that shutdown by 1 day, that's equivalent over a month to about 3% production. That's like increasing the recovery by 3% over that month. Let's remember that. It's not just about optimizing the steady state and how we should be operating, it's optimizing how we do a variety of things in our mines. It's interesting, I've got spills up there. This is, I won't say, I didn't reference where this picture came from because this picture was online. This is a fantastic system to measure frost height, but there's no frost being recovered here. Interesting. Spills, I mentioned spills. I used to do a lot of work in flotation optimization. Almost every mine site I went to, I can only think of one that didn't over a period of 2 weeks, had massive spills on the floor. Trudging through 3 or 4 inches of concentrate on the floor every now and then. I wanted to get a picture of it up there, but funnily enough, nobody takes pictures of that and sticks it on the web saying this is how things happen on the mine site. It's interesting. There's pictures of this is perfect, this is how we operate, but there's no pictures of this happens all the time when there's spills. And the importance of 3D. I've mentioned this a few times, but there's one particular thing I wanted to mention here. Last week we had Autotech come here and give us a talk, maybe the week before. And they talked about one of their online analyzers, I can't remember, something 8. Anyone remember? Courier, thank you. And there was a question saying, what's the maintainability and the sort of, performance of this in terms of continuous operation? And they said, look, the thing works fantastic. The question was, well, but why does it often not get used on site? They said, well, it's very, very stable. It doesn't need much maintenance. But all the pipes and all the sampling points that lead to it always stuck up. And when you design those, and you don't design them in 3D, you may miss the fact that a pipe's actually got an upward thing. That's the only way it could have been fixed. Or whatever it is. That 3D visualization is so powerful when it comes to that everyday operation. And they mentioned that. They mentioned that once they start doing it in 3D, they found that the designs were not ideal for feeding the sample material into this analyzer. So, I'm going to ask again for your own thoughts, because there's a whole world out there in digitisation and virtualisation that is being, for our side, led by Marcin, but we're all on that journey with him. And what should we be researching? Is it digital and virtual twin? There's big data, there's machine learning, there's AI. These are all considerations. There's many there. Many would say, well, mines, a lot of mines don't connect to the internet very well. How can you do this? You don't necessarily need to be connected to the world. You need to be connected inside the mine. And most mines that I've been to are very well connected, or can be very well connected internally. Marcin and I had a discussion the other day, and it was along these lines of what are the research questions. I mentioned before, we've got our EPCs, we've got our consultancies, we've got our groups. We are researchers. There's a lot of challenges out there, there's a lot of opportunity, but what are the research questions? These are questions that we need to answer for ourselves and with the people we work with. And how do we help our stakeholders? With that last point, I just wanted to reference last week's presentation by Don McKee. And he talked about Julius Kruchnitz and how he worked with Mount Isa Mines and Concentrator 1. The whole point of JKMRC was to help people on the site to fix their problems. That's why JKMRC was born. And it's imperative that we identify in some way how we work with our stakeholders to provide that research. I think I just want to leave you with that thought, because sometimes it's a level of frustration, I know it is for me, that sometimes we say, the mining companies don't know themselves what they want, how can we tell them? Well, it's our job to interact with them and work with them to identify what we can do for them and what we can help them do maybe with others. With that, I'll finish and ask questions.
Thanks, Marcin. Any questions on the floor? All right, I'll start.
We got one from